Universe missing matter. Imagine you're at a park, watching a merry-go-round. The kids on the inside are whipping around quickly, while the kids on the outer edge are moving much more slowly. It makes perfect intuitive sense. The farther you are from the center of rotation, the slower you should go. This is basic physics, a rule that governs everything from spinning toys to the majestic clockwork of our own solar system. Mercury, close to the sun's immense gravity, zips around in just 88 days. Distant Neptune, far from the center, takes a leisurely 165 years to complete a single orbit. For decades, astronomers assumed this fundamental rule applied everywhere. They looked out at the grand spiral galaxies scattered across the cosmos and expected to see the same thing. Stars near the bright, dense galactic center should be moving at incredible speeds, while stars on the faint, outer fringes should be plodding along. Then, in the 1970s, an astronomer named Vera Rubin decided to actually measure it. And what she found broke cosmology. It shattered our understanding of the universe and plunged physics into a mystery that persists to this day. When she and her colleague Kent Ford pointed their telescopes at the Andromeda Galaxy, our nearest spiral neighbor, they didn't see what they expected. The stars on the outer edge weren't slowing down. In fact, they were moving just as fast as the stars much closer to the center. It was as if the kids on the very edge of the merry-go-round were somehow keeping pace with the kids right at the hub. This was impossible. The gravitational pull from all the visible stars, gas, and dust in the galaxy simply wasn't strong enough to hold on to those speeding outer stars. They should have been flung off into the void of intergalactic space millions of years ago. The galaxy should have torn itself apart. Yet, there it was, stable and intact. This bizarre observation gave rise to what scientists call the galaxy rotation curve problem. The curve is just a graph plotting the speed of stars against their distance from the galactic center. The predicted curve, based on all the matter we can see, slopes downwards. The observed curve, what Vera Rubin actually measured, is bafflingly flat. It was a cosmic smoking gun. The only way to explain this discrepancy, the only way for that galaxy to hold itself together, was if there was more to it than meets the eye. A lot more. There had to be a huge invisible halo of some kind of stuff surrounding the entire galaxy, exerting a powerful gravitational pull. This unseen substance wasn't emitting light, it wasn't reflecting light, it wasn't absorbing light. It was, for all intents and purposes, completely dark. And so it was given a simple yet profoundly mysterious name: dark matter. The scientific community was initially skeptical. Such an extraordinary claim required extraordinary evidence. But soon, the evidence started pouring in from every corner of cosmology. Astronomers turned their attention from single galaxies to massive clusters of galaxies, gravitationally bound superstructures containing hundreds or even thousands of galaxies. In the 1930s, long before Rubin's work, astronomer Fritz Zwicky had already noticed something strange. He observed the Coma cluster and realized the galaxies within it were moving around chaotically, like bees in a swarm, at incredible speeds. He calculated that the cluster's visible mass was nowhere near enough to keep those galaxies from flying apart. He famously called this missing mass Dunkelmaterie, or dark matter. At the time, his observations were largely dismissed, but now they fit perfectly with the new data. These colossal clusters were behaving as if they were embedded in a gravitational web far more massive than anything we could see. Then came an even more elegant proof: gravitational lensing. Einstein's theory of general relativity tells us that mass warps the fabric of space-time. A massive object, like a galaxy cluster, will bend the path of light that passes by it, acting like a giant cosmic magnifying glass. When we look at a distant galaxy cluster, we can often see the light from even more distant objects behind it being smeared and distorted into strange arcs and even multiple images, a phenomenon known as an Einstein ring. By measuring the degree of this distortion, we can calculate the total mass of the object, acting as the lens. And time again, the result is the same. The mass required to produce the observed lensing is 5 to 10 times greater than the mass of all the visible stars and gas combined. It's like looking at a person through a funhouse mirror and realizing their reflection suggests they weigh 1,000 pounds, even though you can only see a 150-pound person there. The gravity is real, the mass must be real, but it is invisible. The final nail-in-the-coffin piece of evidence comes from the very beginning of time itself. When we look at the cosmic microwave background, the faint afterglow of the Big Bang, we see a snapshot of the infant universe. This snapshot shows tiny temperature fluctuations, seeds that would eventually grow into the galaxies and clusters we see today. Our best cosmological models can only replicate this precise pattern of fluctuations if they include a massive amount of slow-moving, non-interactive matter, dark matter. Without it, there simply wasn't enough gravitational pull in the early universe to clump normal matter together fast enough to form the vast cosmic web we observe. Dark matter, it seems, provided the invisible scaffolding upon which our visible universe was built. So, what is this stuff? We know what it isn't. It's not just dim stars, rogue planets, or black holes. These are made of normal or baryonic matter.
Astronomers searched for them under the banner of MACHOs, massive astrophysical compact halo objects, and found that they simply don't exist in nearly enough abundance to account for the missing mass. Dark matter has to be something else entirely, something exotic that isn't on our standard model of particle physics. The leading candidates are hypothetical particles called WIMPs, or weakly interacting massive particles. These particles would be heavy, explaining their gravitational influence, but would only interact through the weak nuclear force and gravity, which is why they pass through us, our planet, and our detectors without a trace. Scientists are currently operating massive experiments deep underground to shield from cosmic rays, using vats of supercooled liquid xenon, hoping for the 1 in a trillion chance of a WIMP bumping into a xenon nucleus. So far, silence. The conclusion is as staggering as it is undeniable. About 85% of all the matter in the universe is made of this mysterious, invisible substance. The world you see, the ground you stand on, the stars you wish upon, it's all just the 5/6 of the iceberg you can't see. It's a cosmic heist of epic proportions. But as scientists grappled with the mystery of the universe's missing matter, they were about to stumble upon something even stranger, a force that dictates not just how galaxies are built, but the ultimate fate of reality itself. Dark energy unveiled. We've established that our universe is built upon an invisible scaffold of dark matter, a mysterious substance whose gravity holds the cosmos together. It's a mind-bending concept, but at least it makes a certain kind of sense. We see excess gravity, so we propose the existence of excess mass. It's a logical, if strange, solution. But the universe had another, even more profound surprise in store. Because, while dark matter acts as the universe's cosmic glue, there's another, far more dominant component acting as a cosmic accelerator. And this discovery didn't just add a new puzzle piece, it flipped the entire puzzle board upside down. For most of the 20th century, cosmologists debated one central question: what is the ultimate fate of the universe? Ever since Edmund Hubble discovered that the universe was expanding, everyone assumed that the combined gravity of all the matter within it, both normal and dark, must be acting as a brake. The expansion had to be slowing down. The only question was by how much. The universe was like a ball thrown into the air. Would it eventually slow down, stop, and fall back on itself in a fiery big crunch? Or did it have enough momentum to escape its own gravity, expanding forever, but at an ever-decreasing rate, fading into a cold, dark big freeze? To answer this, astronomers needed to measure the rate of cosmic deceleration. They needed a way to look deep into the past and see how fast the universe was expanding billions of years ago compared to today. What they needed was a standard candle. A standard candle is an astronomical object that has a known, consistent, intrinsic brightness. Imagine you're in a dark field and you see a single candle flame. You can't tell if it's a very bright candle far away or a very dim candle up close. But if you know that all candles of this type have exactly the same brightness, you can precisely calculate its distance based on how dim it appears. In cosmology, the perfect standard candle is a specific type of exploding star called a Type 1a supernova. These cosmic fireworks occur when a dense, dead star called a white dwarf siphons too much matter from a companion star, hits a critical mass, and detonates in a thermonuclear explosion of unimaginable power. Because they all explode at almost exactly the same mass, their peak brightness is incredibly consistent. They are the lighthouses of the cosmos. So, in the late 1990s, two rival teams of astronomers embarked on a cosmic race. One, the Supernova Cosmology Project, and the other, the High Z Supernova Search Team, began painstakingly scanning the skies, hunting for these distant, faint explosions. Their goal was simple: find dozens of Type 1a supernova at various distances, measure their apparent brightness to determine how far away they were, and measure their redshift to determine how fast they were moving away from us. By plotting this data, they would finally measure the universe's deceleration and settle the question of its ultimate fate. Both teams worked for years, meticulously collecting data. And when they finally analyzed their results, they both came to the same terrifying, impossible conclusion. The most distant supernova were consistently dimmer than they should have been. They weren't just a little off, they were significantly fainter. There was only one plausible explanation for this. They were much farther away than predicted. For them to be farther away, the expansion of the universe couldn't have been slowing down. In the time it took their light to reach us, the universe had expanded more than expected. The only way that could happen is if the expansion of the universe was not slowing down, but was, in fact, speeding up. It was accelerating. This was a result so shocking, so contrary to all of cosmological theory, that the scientists themselves thought they had made a terrible mistake. They checked and rechecked their data, looking for any possible error. But there was none. The conclusion was inescapable. Something was pushing the universe apart, a mysterious anti-gravitational force that was overcoming the pull of all the matter and dark matter combined. This mysterious force was given the name dark energy, and it is, by far, the biggest mystery in all of science. Unlike dark matter, which clumps together in halos around galaxies and acts gravitationally, dark energy appears to be perfectly smooth and distributed evenly throughout the universe. It doesn't seem to interact with anything at all, except for the very fabric of spacetime itself. It has a bizarre property. It is a repulsive force, a kind of negative pressure that causes space to expand. The strangest part is that as space expands, more of this energy appears, creating a runaway feedback loop. More space means more dark energy, which means space expands even faster, which creates even more dark energy, and so on. Bizarrely, Albert Einstein had actually predicted something like this nearly a century earlier. When he first formulated his equations of general relativity, they predicted a dynamic universe, one that was either expanding or contracting. But the prevailing view at the time was that the universe was static and eternal. To fix his equations and make them match this view, he added a fudge factor, a mathematical term he called the cosmological constant. It represented an intrinsic energy of empty space that would perfectly counteract gravity, holding the universe in balance. When Hubble later proved the universe was expanding, Einstein famously called the cosmological constant his biggest blunder. And yet, here we are. It turns out the leading candidate for what dark energy actually is the energy of the vacuum itself, a modern version of Einstein's cosmological constant. When we put all the pieces together, the evidence from galaxy rotation, gravitational lensing, the cosmic microwave background, and those distant supernova, we arrive at the modern picture of our universe. The cosmos is not what it seems.
All the atoms, all the stars, galaxies, and planets, everything we have ever seen or interacted with makes up a paltry 5% of the universe. About 27% is the invisible dark matter, the gravitational scaffolding holding it all together. And the vast majority, a staggering 68%, is this enigmatic dark energy, the repulsive force pushing it all apart at an ever-increasing rate. 95% of our reality is a complete and utter mystery. This accelerating expansion paints a strange and lonely picture for the ultimate fate of the cosmos. As the expansion speeds up, distant galaxies will be pushed away from us faster than the speed of light. Their light will never be able to reach us. One by one, they will disappear beyond our cosmic horizon, winking out of our observable universe forever. In the far distant future, the night sky will be empty, save for the stars of our own local group of galaxies, a tiny, isolated island in an endless, dark, and empty void. We are living in a special, fleeting moment in cosmic history, a time when we can still see the grandeur of the universe before it all slips away. We are cosmic detectives who have just realized that 95% of the crime scene is invisible, and the clues are disappearing before our very eyes. What do you think this missing 95% truly is?